Now, in a normal distribution, there is a special type of data point, or a unit really, that we refer to as a z-score. And it describes how many standard deviations a particular data item lies above or below the mean. And we can use the following formula to obtain the z-score. Now, data items above the mean end up having positive z-scores, and data items below the mean end up having negative z-scores. If you're talking about the mean exactly, that z-score would be 0 because it has no deviation from the mean. So your z-score is how many standard deviations that data item lies above or below the mean. So let's do some practice here. Sorry guys, oh my goodness, I have so many typos in this one. The mean weight of newborn infants is 7 pounds, and the standard deviation is 0.8 pounds. The weights of newborn infants are normally distributed. Find the z-score for each of the following weights. So again, my formula for the z-score is to take the data item, subtract the mean, and divide that by the standard deviation. So in this case, my data item is 9. My mean is 7, and my standard deviation is 0.8. So 9 minus 7 is 2, and then I go ahead and I do 2 divided by 0.8. I get exactly 2.5 here, or 2.50. Now, oftentimes we do round z-scores to usually 2 decimal places, but again, refer to my math lab, refer to those questions for exactly how they want you to round. But 2 decimal places tends to be the most common. So basically what this says is that the data point of 9 pounds lies 2.5 standard deviations above the mean. And it's above the mean because it's positive, right? So this is positive. All right, let's do another one. So z equals our data item minus the mean over the standard deviation. So my data item here is 7. My mean is also 7, and my standard deviation is 0.8. So what I get is 0 over 0.8, which is just 0. So the data point of 7 pounds lies 0 standard deviations from the mean. And what that means is that 7 is the mean. That's why the answer is 0. Okay, so if your data value is actually the mean, you're always going to get a 0 there because it doesn't deviate from the mean at all. And our last one is for 6 pounds. So here, again, our data item is 6. Our mean is 7, and our standard deviation is 0.8. So we're looking at -1 over 0.8, which is going to be -1.25. So the data point of 6 pounds lies 1.25 standard deviations below the mean, right? And it's below because the sign is negative. So what happens here is when a data point starts out bigger than the mean, like the 9, then you end up with a positive z-score. When your data starts out smaller than the mean, you end up with a negative z-score. So it helps to tell you the direction there of where it lies compared to the mean. All right, so a student scores a 70 on an arithmetic test and a 66 on a vocabulary test. The scores for both tests are normally distributed. Okay, So let's keep going. So a student scores 70 on an arithmetic test and 66 on a vocab test. The scores for both tests are normally distributed. The arithmetic test has a mean of 60. So I'm actually make a note here. Arithmetic. So the student scored a 70. All right, the mean was 60 and the standard deviation is 20. For the vocab test, let's see, the student scored a 66 and the test had a mean of 60, or let's say, and a standard deviation of 2. On which test does the student have the better score? So now if you just look at it for face value, you're probably saying, well, a 70 is definitely better than a 66, right? And obviously it is, but they're really referring to a better score compared to other students as well. So what we can do to compare two things here that are similar, but are a little bit different, right? They're not exactly the same score, not exactly the same standard deviation, is we can use z-scores to compare things. So I'm going to find the z-score for both. So again, I take my data point, I subtract my mean, and divide by my standard deviation. So I get 10 divided by 20, which is 1/2. You do want to be careful. Make sure you follow the formula and always subtract with your data item first. If you don't, your sign will be off and that is going to be wrong. So you want to make sure you always do the data point minus the mean. Now for this one, again, we have 66. My mean is 60 and I'm dividing by 2. 66 minus 60 is 6. 6 divided by 2 is 3. So here I have a z-score of 50. So it means that the score lies 0.5 standard deviations above the mean. And here our score lies 3 standard deviations above the mean. So on the front of it, if we're just looking for the final answer for the student, obviously the student's like, yeah, I would rather have a 70 than a 66, right? Obviously. But compared to their classmates, they actually did better on the vocab test because they scored 3 standard deviations above the mean for the class. Whereas over here, they only scored half a standard deviation above the mean. So even though the raw value was better here, 70 is higher than 66, we actually compare it to what everybody else did in class, looking at the mean, looking at the standard deviation. The student was much higher above the mean here, right? 3 full standard deviations above the mean, which is a lot. So for the classroom, compared to all the other students, this score of 66 is actually much better. So this student probably would have been one of the high flyers in class for this exam, where here, they were probably just a little bit above average, right? They're only half a standard deviation above. Whereas here, compared to everybody else, they were 3 full standard deviations above. So compared to the rest of the group, they did quite good on the vocab test. All right, so one last example here with z-scores. So intelligent quotients, which are IQ scores, on the intelligent tests are normally distributed with a mean of 100 and a standard deviation of 16. What is the IQ score corresponding to a z-score of negative 1.5? Now, this one's a little bit tricky. So here I have the z-score. And I want the IQ score. I want the data point, right? I want the data item. That's different than what we did in the last couple of examples. So in the last 2 examples, we started with the data items, right? The actual scores on the tests or the pounds for the babies, and we went to the z-scores. So now we're going backwards. So how can you go backwards? Well, let's think about our formula. Our formula was, in a different color for a second. Your z-score was equal to your data item minus the mean over the standard deviation. So what I could do here is I can solve and rearrange this equation so that the data item is solved for. So it looks a little bit weird because we're doing it in words, but think back to how you solve fractions, right? The first thing you would do is you would multiply by that common denominator. So I can multiply by that standard deviation on both sides. So now I see that my standard deviation times my z-score is equal to the data item minus the mean. And then what we can do is we can add that mean to both sides. So here you have a new formula if you want to make note of it. And it says that the mean plus the standard deviation times the z-score is equal to that data item value. So in our example here then, I'm running out of room, but let's see, the mean was 100. The standard deviation in this problem is 16. My z-score is negative 1.5. And if I can solve that, that will give me the data item that I need. So I'm going to do 16 times negative 1.5 first. 0.5. And I get negative 24. So 100 minus 24 is going to give me 76. So what's the IQ score corresponding to this value? Well, the IQ score then is 76. So here is a new little formula that you can just kind of keep in mind for when you have to work backwards. So we just took the original formula we have and we rearranged it and we solved it. B says Mensa is a group of people with high IQ scores whose members have z-scores of 2.05 or greater on the intelligent test. So what is the IQ score corresponding to a z-score of 2.05 this time? So I'm going to use my same formula here, right? So I'm going to take the mean, which is 100. I'm going to add it to 16, which is my standard deviation. Now this time my z-score is 2.05 instead, and that will give me my data item that I'm looking for. So I have 100 plus, so 16 times 2.0, 16 times 2.05 is going to be 32.8 plus 100 is 132.8. So my IQ here for the answer would be 132.8. Now, just as a note from your textbook, it does say an IQ score of at least 133 is required to join Mensa. So this gets rounded up to 133 instead here. All right, so again, this is another formula you may just want to keep in mind for those questions where you have to work backwards. So you have the z-score and you have to go back to the actual kind of regular data value that you're looking